And toward the end of it, we started talking about the following, right? So we thought about last time this idea that like maybe based on the set of features that we collected, we can do a good job using a linear function to approximate the sales price, right? But in many cases, if we look at our data based upon the collection of features that we actually predicted, we're not going to have a really nice linear function, right? It's not just this linear function that doesn't work particularly well. No other linear function that we can draw with respect to date of sale does a particularly good job predicting sales price. And by that, I mean that the least squares loss function is reasonably high when we evaluate it on the set of data points that we are trying to use to train a model. Okay. So we mentioned that this could be for any number of reasons, but the primary one that we're going to focus on today is that this might be because the relationship between the collection of features that we gathered and sales price are inherently nonlinear. So as we talked about before, the recipe that we generally want to use when thinking about how we're going to do our entire machine learning pipeline from data to making predictions, first we want to decide on a model. And in the case of linear regression, we were thinking about linear models. This is going to be the primary thing we're going to think about changing today, right? We're going to think about maybe using, for example, a quadratic function, right? Or more generally, maybe some polynomial of degree p. Or something else, right? That's the primary part of this recipe that we're planning to change between now and last lecture, right? We're still going to think about using the loss function least squares, right? And we're not really going to be talking about sort of how we minimize that loss function on the data we have, right? That is a perhaps somewhat more complicated problem if we're thinking about nonlinear functions, right? This really beautiful, elegant closed form description of the least squares minimizer work very well when we're thinking about linear functions. And it's going to take more work, and perhaps that's not the best use of our time in this class to talk about how we do that minimization. Okay? And then when we have a more a function, right, we're going to use it in exactly the same way as we used before to make new predictions for new examples.
Hi, Jamie.
Yes.
Could you tell everyone chat is back online? That they can.
Yes. Excellent. Chat is back online. Yes. So I very much encourage people. I liked last time when people were breaking in and giving and having verbal questions. You're also more than welcome to type a text question into the chat box, and our awesome collection of TAs are going to do their best to respond to those in real time. And we very much encourage you to use that if you have a clarifying question, but we don't recommend you try to follow the chat at the same time you're following the lecture. Right? It's just going to be individuals asking clarifying questions in the chat. Also, you can either jump in and ask me a question just by unmuting yourself when you think the time is reasonable, or you can type hand, and we're going to hope that that will be like easy to receive between the other things that are going on in chat, and the TA will call on you, and then you can unmute and ask your question if you prefer to do it that way. Okay. Does anybody have any questions about that logistically? We're doing something quite similar to what we were doing before. I'm just sort of encouraging people to not follow the chat as though it's containing a bunch of extra critical information for everyone. It's individuals clarifying questions. Oh, sorry, got a chat. Okay, it might have covered in class. Okay. So what I was saying when I was looking at, this slide, was that I was saying last time we talked about deciding on a model, choosing the loss function, figuring out how to find a function that fits our model, which minimizes the loss on our data. And a good bit of the time we spent in the last class, we used actually showing that we can find the least squares estimator if we're thinking about a linear model for our data, right? There's this nice closed form solution. And we're not going to be talking about precisely what the process to find the function which minimizes loss on data will look like if we're thinking about these more complicated models, quadratic or polynomial, for example. Okay, great. Okay, good. Okay, so as I promised, right, we're now going to be thinking about perhaps more complicated functions of the features that we have gathered and using those to make predictions about sale price, right? And for example, one thing we might think about is quadratic functions, right? And I think we briefly saw this slide last time, right? That this slide basically has, we're assuming that in this case, our sale price, yi, can be approximately predicted from a bunch of linear terms, right, of our features, along with their squared representations, right? So this is just a quadratic function of the collection of features we've gathered. Okay. So that, in that world, we're deciding that our hypothesis or that our model, we're assuming that we can do a reasonably good job predicting sale price from the date of sale using a quadratic function. Okay. Apologies, there's something funky going on here. Okay. More generally, we could think about the model that we're using to be not just a quadratic function, right? There's nothing particularly fancy about quadratic functions, right? They are a generalization and something more complicated than a linear function. But perhaps you would want something actually which was a higher degree polynomial than degree 2, right? There are certainly going to be circumstances where your data set would be really nicely fit by, for example, a degree 3 polynomial or a degree 5 polynomial when compared to a degree 1 or degree 2 polynomial, okay? And here we just have, the weights here, just like before, are sort of the things we would be optimizing over to try to minimize our loss. And xijl are simply the ELF powers of the features we're seeing for example I, for house I, when we're looking at feature J. Does that make sense? Okay, great. I know there was some clarification questions about the notation last time. Okay. More generally, we could actually think about an even more general class of functions than degree P polynomials, right? We could think about taking our measurements of houses, right? Xi just represents the feature vector for house I. And we could think about using p different functions, h1 through hp, to transform those in some way, right? And I'll give a couple of examples in a minute. But we could think about taking our initial representations of our houses, transforming them into some other p-dimensional space, and then looking at linear functions, right? Again, these linear weights over those representations. Okay, great. Okay, so as I mentioned before, right, we're now thinking about various generalizations of this when we were thinking about linear models before. But I want to think about the loss function continuing to be least squares, because it has some nice interpretations for the rest of this lecture. Okay. So the regression problem that we're talking about, right? We're thinking about taking some mapping H, which takes houses in RD, right? Remember, we initially had d-dimensional representations of our data points, and maps them into RP, right? Some other p-dimensional space, which might be higher or lower than D. And we can just represent that if we're thinking about D equal to 1 and H being a mapping from one dimension into all of the p up to p powers of x as this nice collection of equalities right here, right? H can take x and actually transform it into a vector of x squared up through xp, the different up to degree p powers of x. Okay. In the case where D is larger than 1, right, or even in the case where D is 1, we could think of all sorts of complicated things that H could do, right? H could map our x's, H could map our x's into some much more complicated space if we wanted them to, right? For example, we could think about some fixed weights, uj from 1 to p, and we could, for example, think about hj doing some nice weird exponential mapping of our x's, right? Or we could think about just some simple thing where we're looking at quadratic terms, right? Or we could think about using some kind of cosine function to change the representation of our x's, right? And this is just a way of imagining that, like, maybe there's a more interesting way to represent x as a function only of x, right? That still allows us to think about like the linear function at the end that we were originally talking about, right? Because we're still going to be thinking about linear functions of h1 through hp. Okay, does anybody have any questions about that? Okay. Oh, sorry, go ahead.
I have a question for the D equals 1 part. So you have like h sub 1 of x equals like x, and h sub 2 is x squared. So I guess that's kind of like just like one example of a function to like transform the data, like apply to the data. But I'm just confused about I guess the xi's in that. So I guess because it's only one.
Sorry, you broke up just at the end there. Because it's only one dimension?
It's only one dimension. So basically the first data point is just like chain data point is squared, and the third, or like the pth one is taken to the pth power. Is that kind of the interpretation of that particular transformation?
Yeah, so if you think about applying h to our entire data set x, right? Maybe this will help. If we think about applying h to our entire data set x, right? Our entire data set x was a matrix, but it was a one-dimensional matrix, so it ends up looking like a column, right? So then what we end up getting is xi to the d, xi to the p, right? We then end up with this nice matrix that actually that maps each of our initial one-dimensional points into their pth powers. And now each row, which used to be, it still corresponds to the same house, but rather than having a single numeric representation of that house, we now have that numeric representation and all of its up to pth powers. Is that helpful?
Yeah. Okay. Thank you.
I have a quick question.
Yep, absolutely.
In regards to what if you have a feature, like multiple different feature vectors that can be mapped by different representations? One can be linear, one can be polynomial, et cetera, et cetera. What do you do in that situation?
I think I don't totally understand your question. So I guess maybe a rephrasing, and you can tell me if I'm wrong, of that question is the following. How do you choose which of these different ways to transform your data if you could choose linear or quadratic, or one of these other strange mappings H, right? Is that the question you're asking?
Well, I was just more saying if you have a house and you represent it, let's say in terms of square feet and in terms of date sold,
Mhm.
as shown earlier, square foot could be a linear correlation between price, while date sold could be quadratic. So what do you do if you want to represent the house in terms of both?
Yeah, so we could certainly think of an h that does that, right? So we could say that h1 of x is equal to x1, right? If the first dimension was square feet, and h2 of x is equal to x2 squared, right? We're not sort of forcing ourselves to use the same functional form for each hi.
Oh, okay, I understand. Thank you.
Yeah, good. Right. So that's a very good question, right? We certainly don't have to think only of representing each of our features and sort of the mapping our features in each of the same in the same way. Okay. All right. Great. Okay. So the thing that's primarily different now is that we're not necessarily going to be thinking about a linear hypothesis. I mean, we are, but we're thinking about it as linear in something other than our original data, right? Our original function was just a nice linear function of our original data. And now we're thinking of the hypothesis or the collection of models that we're looking at to be a linear function, but of this transformation of our data. Right? Okay. I still want to think about loss as least squares, right? And that looks quite similar to what we had before, right? We still have that we're looking for each of our data points at the true sale price, yi, and then we're looking at our prediction, right? Based on the features, we transform our features, and then we use this linear function that we've decided upon, right? And that gives us a predicted sales price. And what we're looking for is just looking to minimize the sum of those squared differences. Okay. So it looks like there's a bunch going on in the chat. Does anybody have a question here? All right. Okay. So, right, in this case, one thing we could think about doing is using some small number of dimensions, right? Our mapping could have some small number of dimensions into which it's representing our houses, right? And you might see some nice, right? The W that we learn might, and the function hx transpose w might have this nice form that looks like this orange curve right here, right? If p is reasonably small, right? And this looks something like a quadratic, right? So you could imagine that like the particular h that generates this is actually the h that represents date of sale as both a linear and quadratic term, and then we're looking for weights on both of those terms that sort of does a nice job in terms of the least squared estimate, okay? On the other hand, right, we so far haven't constrained ourselves in any way, right? We're just saying H maps our data to some p-dimensional space. It could do that in an arbitrarily complex way, and p could be very, very large, right? Rather than just thinking about p being two-dimensional or something like that, right? For example, right, we could think about a large p, right? A p that is something on the order of n, right? And if p is on the order of n, right, we can remember some basic facts from like, some algebra classes we've taken, but like we can always define a p degree polynomial to go through any p points or maybe p minus 1 points, right? So if we think of p, this space, the dimension of the space into which we're mapping our data points as very, very large, or at least relatively large compared to the number of data points we have, right? We'll be able to find some w, right, when we're minimizing our least squares error over our data, which does a very nice job exactly estimating the sales price on our training data from date of sale. Does anybody have any questions here? Okay. So I have I'm going to see how this goes. Apologies if this is like a huge disaster. I would like everyone to fill in this poll that I'm going to put in the chat. Okay, which is just asking people to guess or say something about whether they like which of the two solutions, a large P or a small p, they like better. Ah, it's working. All right, I'm going to give everybody a minute or two. Can you guys see the responses?
Are you asking like which one is better in terms of the fit or the final usage?
I haven't specified.
Okay.
Okay. And Kevin's saying, no, you can't see the results. I don't know how to, here, one thing. I don't know how to show you the results. Okay, but I probably could. Yeah, so I can tell you that of the people who responded, we've kept roughly, definitely a pretty large majority said that B is better, right? We had a non-trivial fraction of people who said A was better, right? But I haven't said what I mean by better, right? I just like drew two graphs and I asked you, which is better? Well, maybe one's aesthetically more pleasing to you or something, but I haven't given you a formal way to compare these two different models that we've learned over the same data, right? Okay. So what is our goal anyway, right? What is our goal for picking between different models, right? We had these two different models. One's this nice smooth function. One's like a pretty jaggedy thing. But if we looked at, for example, like our least squares error on the two different graphs or on the same data set for the two different functions, we'd see that the least squares error is lower on the more jaggedy thing on our training data than was on the other one. So now I want to ask another question. And I want to ask you guys to write a little bit about why you think one is better than the other. So I think the same, let's see if I lock this. Okay, so if you go to the same poll link, which I'll mark here again. If anybody wants to write, cool. Some people are writing stuff. Excellent. See if I can pull up I can probably pull up the, okay. Apologies. Okay, so I can tell you a bit about what people are writing here. I'm seeing larger P seems to be overfitting. B, it's better for guessing new data. Large P fits well for specific data set, but not for all, might be overfitted. Small p is more general. Smoothing helps make predictions for B. B, because it generalizes better. B tracks the trend of the data. B, small p will handle new data better. Large P is more biased. A is overfit. A is an abhorrent overfit. B is actually low dimensional. Depends. Small p is better since it will generalize better to new data. Okay, so informally, what a bunch of you are saying is, let's see if I can pull this back down. Excellent. That P is lower dimensional, right? B is lower dimensional because we're thinking of P as small, and A is larger dimensional, right? And that B sort of grasps some trend while A is overfitting whatever that means, right? Okay, and we haven't really talked precisely about what any of those things mean. So we're going to talk a little bit about that today, right? Great. Okay, So, as I mentioned before, right, if we're thinking about A, the least squares loss that we could compute on our training data is actually 0 here, right? We're exactly predicting the sale price from the date of sale for every one of our training points. On the other hand, if we're looking at B, right, our least squares loss is greater than 0 on our training data. So that's certainly one way in which A is better than B, right? A has lower training error. A has lower least squares loss on the training data that we have than B. Okay. So, least squares loss on training data, we're often going to refer to that as least squares training error, or even, we might even ignore least squares and just refer to, if we have a loss function that we're considering for the remainder of the class, that'll be least squares, at least this class, this lecture. And we'll refer to a model, a hypothesis's training error as how much error we see that model makes when making predictions on the training data, okay? So the training error of the large P model is lower than the training error for B, okay? On the other hand, there was a vast majority of the class. Oh, interesting, people are still answering this question, cool. I'll have to look at like the large collection of things when people are done. I just saw it in the background. Okay, so, right, so if we want to talk about why B is better, right? B is this nice function that seems to be like doing something that's capturing a general trend in the data and not sort of jaggedly hopping from house to house, right? So a lot of the answers people gave suggested the thing that was really problematic about A compared to B was that we wouldn't have as much to be able to say about predictions that we're actually caring about, right? The whole reason, or at least a large part of the reason that we're trying to learn some model over our data set is that we'd like that model to do well predicting sales prices for new houses that come on the market, right? So if we think about some new house that goes on the market and its date of sale is sort of here, right, relative to the other data points. If we look at the prediction that the model A makes, right, it makes this prediction right here, right? And compare that to the prediction that we'd make using model B, it would be here, right? And you guys can probably see that these are fairly different in terms of sale price, right? By maybe, I don't know, 20% or something of the sale price on B. And the interesting thing here is that if we're looking at model A, can anybody tell me sort of, or maybe I'll explain this. Okay, so for model A, only this part of the model seems to have anything to do with the prediction we're making for this new house, right? So basically, model A is only looking at 2 previous data points to make the prediction for this new house, right, for sales price. Those are totally governing what we're saying. The XY pairs that are sort of closest in X space are governing what we're going to predict for sales price. On the other hand, right, there's not some obvious pair or even triple or set of K much less than N points from our original training set that seem to be governing precisely what our B model says, right? It seems to be that like much of our data, right, much of the data in our data set seems to be mildly affecting the entire function of B, but that no one data point is really, or even 2 or 3 or 4 data points are primarily governing the prediction we'd make for a new house on the market if we were using model B to make predictions. Does anybody have any questions? Okay, right. So this is one way in which, right, and I'm not saying anything formal here. I'm just saying that for model A, only 2 previous houses are governing your prediction for any new house. And for model B, it seems like some more global property of our data set seems to be governing the prediction that we're making. Okay, so what do we mean? Oh, sorry, there was one thing other here. right? Our goal primarily in much of machine learning is to make predictions for new houses that look like the houses in our training data, right? And by that, I just, informally mean that if the initial training data was sort of intentionally restricted to only consider houses in the Seattle area that didn't have a swimming pool and that were within, these various collection of zip codes, we wouldn't expect our model to do a particularly good job on a new house that has a swimming pool that's in Los Angeles and is in a totally different zip code than any of our training data. Right? But to be a bit more formal, what do we mean by look like? What do we mean that we actually want the house that we consider or the houses that we consider that we're making predictions on to look like our training data, and that the goal for the model that we're picking is that it will do a good job predicting on those new houses that look like our training data. Okay. So we're postulating that there exists a distribution, or if you think about the entire collection of houses we might ever observe, that can be described as a distribution, a joint distribution over the date of sale X and the sale price Y. Right? And that's a fairly complicated distribution, right? This is intentionally looking like sort of a point cloud rather than a finite set of points, right? Because there may be many, many, many more houses than we'll ever actually see. Okay. So on average, when we think about a house drawn from this distribution, it will have some date of sale and some price it will or has sold for. And we want our model to do a good job predicting sales price from date of sale for a random draw of a house from this distribution. Okay. And as I'm mentioning here, right, we're not going to be able to do that, or it will be very difficult to do that, if our training data doesn't also come from the distribution where the new predictions we're going to want to make are coming from. Okay, so for the remainder of the talk, we're going to talk a little bit about sort of a formal sense in which why model A has more problems than model B, right? We sort of informally said that it seems to be overfitting, it's high dimensional. I said something about the fact that any of its predictions sort of only seem to depend on 2 of the training data points compared to B, where it's a smoother function, and any prediction it makes seems to be not overly governed by any pair of data points or small number of data points. It seems to be sort of some aggregate statistic of the training data. Okay, so the way we're going to talk about that is we're going to talk about something that's canonically known as the bias-variance trade-off in machine learning. And it's fine if you don't know what that means. We're going to describe that in some more detail here. Before I do that, does anybody have any questions about the prior part of the lecture?
Yeah, I have a question.
Yeah, great.
So in the previous slide showing the point cloud, you mentioned that so I just want to know, why is the point cloud so dense? You mentioned some reasoning behind that.
So I didn't really mention like what why this point cloud has like density in some places and not in others. I'm just let's assume that there is some correlation between date of sale and sale price.
Okay.
Right. The correlation will generally look like some density in this space as opposed to uniform spread across the entire thing.
Okay. Okay. All right. Thanks.
Yeah. Right. Sounded like somebody else had a question. No? Okay. Apologies. There's some lag. So sometimes I hear a small amount of something and it's not clear to me whether that's someone who has a question or just some lag for something else. Okay. All right. So now we're going to talk a little bit more formally about this bias variance trade-off, which will give us a formal way to describe why this model A, this high dimensional P, will sometimes have more problems than the lower dimensional P. Okay. So in much of machine learning, right? Our goal is to predict y given x, right? To predict the sales price given the features we observe, and for example, the date of sale or the number of square feet, right? And we postulate that there exists some distribution over xy that we may or may not have direct access to. And in general, we assume we don't have direct access to that, right? Okay. So more formally, right, we're generally looking to find a function eta that minimizes our loss, right? And if we're thinking about least squares, this will be the loss that we're looking to minimize, right? And in the last couple of classes, right, today and Monday, we were thinking about linear functions of x, right? We were thinking about etas, which were linear. And today we've introduced this idea that we might be thinking about degree p polynomials of x, or some kind of linear generalizations of x into p dimensions, right? So what we're doing is we're looking, we're ideally trying to find some eta which does well on a new draw xy from this distribution pxy. All right, so if we think about this sort of as a point-by-point process, right? We're trying to pick a we're trying to pick a function eta x, which minimizes the squared error for that particular point, right? And if c is in 0, 1, right, or in whatever range we're thinking about for y, right? Let's suppose y is in 0, 1, but y can be more general. Right? The way to solve this, if we're sort of conditioning on x, right? So we're thinking about eta, and we're saying, okay, if we're not thinking about eta being a function that's sort of restricted to some class, we can decide what value we want eta to take for every input x, right? And really what we're trying to do is do a really good job predicting on every x. So we can think about, apologies. We can think about what exactly it's going to look like to predict for a particular x. And in general, if what we want to do is minimize our squared error for a particular x, that's equivalent to just predicting the expected value of y when we condition on x given x, right? So if we know a particular x, right, a particular date of sale, and we're trying to just minimize our squared error for that, and we actually knew this distribution pxy, what we'd want to do is we'd want to predict the average sale price of a house with that date of sale drawn from the original distribution. Okay, so what that means is under least squares loss, the optimal predictor just does this nice thing where it says, given an input, what I'd like to do, you know, if I had infinitely much data, this isn't something we're actually able to do, right? It will just predict the average value of our output variable, in this case, sale price, of the houses that have the date of sale x. Okay, this is some function that can be defined in terms of this entire distribution, but it's not one we directly have access to, right?
Professor, I have a quick question.
Yes.
So I understand the last part, like we're predicting the average value of x given average value of y given the data we have.
Mm-hmm.
But how is that gonna minimize the least square? Like I'm confused about how is that the minimum?
Right. So I think the term you need to look at is this one, right? And you need to think about what c you'd want to place here to minimize this quantity. Because this is a squared term, it's always going to be strictly non-negative. If we set c to be y inside this term right here, then this is 0, right? This term right here will be 0. Which means that we'll be able to minimize y minus c squared by setting c equal to y, right? And this is all conditioned on x equals x, which will mean that the minimizer of this thing, which is just the squared error for a particular x, is equal to c being equal to y conditioned on x equal x. Does that clarify?
Yeah, so c equal to y, but in the right hand side we just wrote y, right?
On the right hand side here?
Yeah.
Right. So we were looking for the argmin, right? So we were looking for the c which minimized this quantity, right?
Okay.
And c, does that clarify?
Yeah. Makes sense.
Okay.
Thank you.
Right. Like
Yeah.
C is just representing the cost of an actual house, right? Like an actual point.
Mm-hmm.
Okay.
Okay. Great. Okay. So, sorry, just looking at this. This is what we already talked about. Sorry, I have some funny thing that's happening here. Okay. Right. So our goal is to predict y given x, and what we showed just before, right, is if we're thinking about this least squares loss term, then the way to minimize those terms is to condition on x equal x and pick the best term there, right? But by the law of total probability, this term right here is equal to this, right? We can just think about conditioning on all the different values of x it might take, and then taking the expectation over that. Okay, so we're trying to minimize this quantity, right? And we know the right eta to minimize it. This was just the slide we had before. Okay. So, okay. So what we know is that if we think about this point cloud again, what is this asking? It's saying that what we'd like to do is minimize this loss, the squared loss. And for a particular x naught, apologies, these transitions look not so great on I'll make these better next time. Okay, so for a particular new point x naught drawn from this distribution, what does this conditional distribution over y's look like, right? It looks, that's just like asking for this slice right here, right? Actually, I'll do that in a better color. Right, so this particular line corresponds to that point cloud. This is just a distribution over y, right? Okay, so for a particular new house price, we can think about the conditional distribution on y that our joint distribution over pxy gives. Similarly, for a different point, x1, right, we'll get a different distribution, right? A different distribution where we condition on that particular date of sale, right? And if you look at this point cloud, right, there's a lot more density for lower values of y than the previous example we gave, right? So that's why this particular curve has much more density for low sales prices, right? Houses that sell in November, in this example, might generally sell for a much lower price than houses sold in April or May. Okay.
I have a quick question.
Yeah.
That distribution that you wrote, is that the distribution of prices along that specific x1, right?
Yeah, that's right.
Okay.
That's right. So like I'm very bad at both geometric intuitions and drawing, but what I'm thinking for, let's think about this second example, right? You could other color again. You could think about sort of the probability mass along this line, right? And that's this. Right. That helpful?
Yeah, thank you.
Any other questions?
By XO and X1, those are new data points, right?
Yeah.
Or are those features?
They're
Okay,
new.
okay.
They're new data point. Well, so they're kind of both, right? So X naught represents the collection of features for a new data point, and X, they're both. They both are representations of new houses in the feature space we're thinking about.
Okay, thank you.
Great. Yeah, and this is one thing that's like often a little confusing, whether we talk about a new data point as like, it's a set of features, right? But it's representing something, which is presumably in this case like a house we're trying to talk about the distribution over sales prices for. Great. Okay, so what are we doing picking a function like we were talking about before, right? Eta x is sort of finding the densest part of this region and mapping it out, right? And if you have or similar, it's not exactly, in this case it might be the densest region, but generally it's trying to make sure about half of the points are above it and about half the points are below it, or at least it's equal to the expected value of the points above and below it at every point, right? And in this case, it happens to be that we have this nice, like, really dense region right in the middle, okay? Okay, so ideally we're looking to pick an eta x that is equal at each point x to the expected sales price, right? And that will be true, that will give us sort of, that will mean that we have these 2 points here that nicely, sort of the average value, the average sales price for x naught and x1 both lie on this curve. Okay, so that's what we would like to find, right? This eta x would give us 0, it would give us 0 squared error, right? Of this particular form that we'll talk about in a second. But what's the problem with this, right? This is all hypothesizing that we have this nice access to this really dense point cloud, right? Where we have many, 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 many examples. In fact, perhaps like all of the examples we might ever see in the future of all the houses that we're referring to. We really only have samples drawn from this distribution. Okay, so what that means is when we're trying to make our model, right, we have, maybe the last 100 days of Zillow data, or the last, 10 randomly drawn houses for the last like 2 years per month or something, right? So we have some data, but we don't have data about every house that might ever sell in the region that we're talking about, right? We have some finite number of n samples, right? So the question is, how do we find some function that approximates eta x when we don't have perfect distributional access to pxy? Right? When we instead, this picture is somewhat, this picture suggests that we might have all of the information, the red line, the purple cloud, and the pink dots. And that's not actually what we have, right? All we know is the pink dots. And ideally, we would like to learn the red line, or even better, the purple point cloud, because if we had the purple point cloud, we could back out the red line. Okay. So what we have is this collection of IID points drawn from this point cloud, or this distribution. And we're generally considering only picking a function that maps from x to y that's, for example, linear, or in this case, quadratic, maybe, right? And what we've been doing thus far, at least for when we were talking about the linear case, we were thinking about picking the function which minimizes squared error over functions in our function class, right? So this could mean f is the set of linear functions. right? Or quadratic functions. So what we'd ideally like to do is minimize this quantity over the distribution. We don't have distributional access. We only have n samples. And furthermore, for any number of different reasons that perhaps we haven't described to you yet, right? We're not actually thinking about designing an arbitrary function to minimize squared loss, right, over our data set. We're actually thinking about minimizing our training error, fixing a class of functions that is fairly restricted. Okay. Anybody have any questions about that?
Just a quick one. So the eta, like, is that also like estimation? So it's not, but it's like the better estimation, right?
So eta is equal to the true expected sales price for a fixed x. So there's no estimation per se. It is equal to the average sales. Eta x is equal to the average true sales price of a house sold on date x. Right? It's true that it won't be correct for every house, but on average, it will be the best thing.
Okay, so when you say we do not have enough data, so we just pick some sample data. So it means when you do the estimation based on this, it's worse than the eta, but eta is the best we have, like ideal. But it's not like, okay, I think I get it. Thank you.
Great. Anybody else?
I have a question.
Mhm.
Yeah, can you go 2 slides back
Mhm.
where we had that curve? Yeah, this one.
Yes.
So instead of, I know that we don't have the point cloud, but maybe this is a hypothetical question. If we had the point cloud, instead of predicting or learning the red line, is it possible to learn a stochastic model which would, given an x naught or x, would give me a value which is not the mean of that, but sampled from that, the normal distribution which you have on the right?
Sure. I mean, yeah. So for example, if you knew this point cloud, you knew the actual distribution, right? And you had like a lot of computational power or like sample access to this distribution. If you wanted to predict the sales price of a house sold on November 3rd, one thing you could do is draw samples from that distribution until you saw some houses that were sold on November 3rd, and then predict their average or predict the first one you see. Or if you had like sort of more direct distributional access, you could just ask, what is the distribution for sales prices? And you could sort of make predictions, like stochastic predictions that are drawn from that distribution.
Thank you.
Great. Okay. So, right, we're doing some optimization here where we're picking a function from our restricted set of functions, right? Linear, quadratic, degree p polynomials, these generalized linear functions in p dimensions, something like this. And we are minimizing our squared training error, right? But we actually care about our squared error on future points, right? This f hat is it's a function of our training data. And then we're thinking about drawing a new data point from this joint distribution, applying our function that we learned on n data points to that new random variable and looking at our error. Okay. So I think it's worth thinking about the following thought experiment, okay? So when we think about f hat is the model we learn for a particular set of data that we've trained upon. And if we think about sort of rerunning the collection process, where we get, suppose our sample size is 100 and we have 100 examples and we use those to train a linear model, right? We'd get some function. And then if we thought about sort of gathering 100 new samples in the same way as the initial 100 samples and picking a model that minimizes least squared error on that new data set, right? Doing so would result in a bunch of different curves, right? If we weren't thinking about linear functions, but like quadratics, right? Depending upon what data we got in that draw initially, right, we'd see slightly different models that would minimize our squared training error. Right? So this is just drawing many of the different models we could have learned, even if we're using the exact same collection of functions. And we're doing the same minimization in terms of caring about squared error. But we're thinking about the sort of hypothetical thought experiment, or maybe not hypothetical thought experiment, where we actually draw a bunch of different, 100-point samples, and we think about doing the same minimization, picking a quadratic function that minimizes squared loss on each of them. Right? And that will give us sort of a natural distribution over quadratic functions which minimize their squared loss on their training data. Okay. So, if we were able to do that arbitrarily many times, there would be some average value, right? Some average function here that would it would represent the model we would learn if we sort of did this thought experiment many, many times and then averaged the values together. So this quantity is something a little bit funny, right? It's not something we have direct access to. It's sort of thinking about like if we drew a random sample, right? Not the sample we have, but we drew a random sample. What would we expect the function f hat to look like? Okay. Does anybody have any questions about that?
Teacher, I have a question. Oh.
No, you can go ahead. Go ahead.
Okay, thanks. Can you go back to slide page 52? In the bottom, you said we care about future predictions, and both here, both x and y are the predicted predict data. So both of them are unknown before we. But both of them serve as random variables, and we care about the expectation here. Can I understand this in terms like we want the expectation of this, the joint expectation of x, y to equal to something, or what do you mean by care the expectation? Like you want it to be small, you want it to be big, or
right. So maybe I'll talk a little bit about this and see if it clarifies it, because I'm not sure if this will be an exact answer to your question. So what I mean by that is we consider a random house drawn from this joint distribution xy. Right? That has some value x, it has some date of sale, and it has some price. But we can imagine if we draw that random point from the joint distribution pxy, and we just look at the x, right, which is a random variable, but we just look at the x and we apply our model to x, that makes some prediction. And then we compare that to the actual sales price for that randomly drawn example. Right? So for any particular date of sale, there's still going to be a distribution over sale prices, right? So it's sort of important that we think about this distribution jointly. And what we care about is having low error on an average point x on its average sale price y. Is that helpful?
Yes.
Great. Okay, there was another question.
Yeah, mine was between the relationship. So you were talking about, okay, let's say we take these 100 samples and we get some sort of quadratic relationship between x and y on these 100 samples. And then we continually take new sets of samples and find the mean function between all of those lines, right? those quadratic relationships. Does that approach the line that would be created if we took the point cloud, like on the previous slide where you had the blue x1 line and you had distributions for all of the different x values with this hypothetical, like we know all data? Would this approach the line that goes through the median, or sorry, the mean of all of those normal distributions?
Yeah, so that's a good question. And the short answer is not necessarily, right? So it's going to depend on what the class of functions we're maximizing over looks like, right? So I'm currently maybe making our lives a little too easy, and that I'm thinking about, this point cloud has this nice sort of quadratic looking dense middle region where a majority, where it looks like sort of the average value of any point, if I take a slice, is nicely in there, and that sort of traces out a nice quadratic function. In general, the point cloud we have may be really not nice, right? The distribution over x and y might not have anywhere near so nice of a dense region. And the collection of functions we're picking from based on our training data might not naturally fit into like the nice dense middle region, even if there was one, right? So for example, if we look at this point cloud and we thought about picking a linear function, right? Okay, so, great. Okay, so now we're going to talk precisely about sort of when we're doing this optimization, when we're trying to decide, okay, so we've picked the loss function least squares, and now we're sort of thinking about this picking a model, right? Which model should we pick? Should we pick linear functions? Should we pick degree p polynomials for some small p, some degree p polynomials for large p? Which of those should we do? And we're going to give like a nice description of sort of where the squared error on a future data point comes from. Okay? So as we mentioned before, right, this is sort of the thing this is sort of the idealized optimizer that we'd really like to have, but we don't have access to. And instead, we learn this function f hat, right, from a particular set of n samples. Okay. So if we think about the difference between the true label y for a randomly drawn y fixing some x, right, conditioned on x, and we think about the prediction we're actually going to make, right, where we think about sort of that average prediction over the set of samples that we draw to learn f, right? Okay. So we can do something simple and just add and subtract a to x from that term, right? We haven't changed anything here. We've just added and subtracted the same term. Okay? And we're just doing a nice complete the squares, which allows us to say, right? Sorry, that didn't work. Okay. So I apologize. These are not so, these don't look so great. Okay. Okay. If we complete the square by noticing, if we have a plus b squared, that's equal to a squared plus 2ab plus b squared, right? So we can just rewrite this term as this one, right? And the reason we're going to do that is it's going to give us a nice interpretation of how we can sort of interpret the error that our estimator f hat d is making on average, okay? So what is this thing, right? We have the expectation of y given x, the expectation of d of y minus a to x squared, right? Given x equals x, if that's here. And then we have these two other terms, right? But this one apologies. Sorry. Right. So this term right here is going to end up here, right? This is b squared, a squared. Now, this term here is sort of the only one that's remaining, right? And can anybody tell me what they think will happen with that term? Does anybody have some intuition for what that is? And why it might not appear on the next line?
Because of the conditional expectation.
Yeah, so y so y minus eta x in expectation is 0, right? So that's yeah, okay. So if we're looking at this sort of conditional error of our estimator for a particular x, it's equal to this pairing of things, right? And let's try to interpret these. This first one is saying, let's look at y minus eta x squared given x equals x. Okay, so that has nothing to do with our f hat at all. That's just saying, okay, whatever y we were looking at, right, for a particular, we pick a particular x, we condition on it, and we look at the distribution over y, right? So the eta x we were thinking about, despite, you know, if we're thinking about a deterministic function, not Sahil's function, right? Y is just some number. It's, you know, or sorry, eta x is just some number. It's equal to the expected value of y given x. Whereas y actually varies, right? When we were thinking about conditioning on a particular value x from that point cloud, there were many values y, many sales prices for any particular date of sale, right? So there is going to be some difference between y and eta x. This is just equal to sort of how much variability there is in sale price fixing a particular date of sale. Okay. So this is what's called irreducible error. It has nothing to do with the optimization we're doing, right? It doesn't have an f hat at all. It's merely a function of this eta x term, which is sort of defined by the distribution and has nothing to do with us, and the distribution over y. The other term, this one right here, what does this look like? Does someone want to try to give me a description of what this is?
That looks like the variance in the distribution over your function approximations given the particular data set that you drew.
Yeah, that's right. It has some flavor of variance, right? And it's, you know, if we ignore the squared term and we just look at the inner term, right? This is sort of saying, how much does our estimation vary from sort of the average value for a particular x? And, you know, this is sort of the squared error term that's related to that, right? So this particular piece, right, I want to erase this. Kind of messy. Okay. So so the point is that this term definitely has to do with the estimation that we were thinking about doing, right? It depends on this f hat. And it's what's often referred to as learning error, right? And when we're going to sort of derive a little bit further another interpretation of this term, because it's actually governed by a couple of things simultaneously, right? It can either be that we're choosing models from some class F that is not complex enough to learn the relationship between x and y, right? Whereas eta x was not constrained in any way. Eta x can have an arbitrary relationship between x and y, whereas our f hat is usually, so far we've been thinking about picking it from, you know, a class of linear or maybe quadratic models. But it also might be the case that the f hat we're learning jumps around a lot from sample to sample because we don't have enough samples to get, the collection of orange lines that we were drawing might just vary a lot from sample to sample, because the optimization we're doing is sort of pulled very far by different samples,
Hi,
which
Jamie.
is suggesting,
It might be easier for you to explain rather than we type in the chat. Could you explain how do we get rid of 2ab, and also what's the relation, like the difference between f hat and eta?
Yeah, so let's start with the first one. What's the difference between f hat and eta, right? So eta is this hypothetical thing, which is representing, so eta is a function from x to y, and eta takes the average value of y for a particular x. So if I had like perfect information about the entire distribution over houses, right? Eta of November 3rd would be equal to the average sale price of every house sold on November 3rd. F hat, on the other hand, f hat is some function, perhaps a quadratic function, that we fit to 100 data points, right? And f hat of November 3rd could be some other quantity, right? That's not going to be exactly equal, almost certainly, to the average sales price of all the houses that were ever sold on November 3rd, right? Because we only had 100 data points and there are 365 days, there might be a pretty good chance that we haven't even seen a single house sold on November 3rd. And perhaps November 3rd is a very weird day relative to other days. Okay, does that help with the first part?
Yes, I think it's pretty well explained.
Okay. Yeah. Okay. Okay. So the other question was how we get rid of 2ab.
Right.
And I want, because of the limited space on the, so expectation of 2ab. This is the expectation of y given x. Is equal to the expectation of y given x of, we'll take the 2 out, y minus eta x minus f hat of x. Okay. And I think it's a good exercise to think about why this disappears, but I will write it in the final notes. Okay. Okay.
I have a question.
Yeah. Mm-hmm.
So from the like, how does the final equality, like the expectation is over like d in the second term?
Mm-hmm.
Like in the previous step, it was over like y conditioned on x. Like how do you move to like expectation over the distribution?
Yeah. Oh shoot, maybe I screwed up what I wrote here. I think I wrote.
If you look at that top
Yep,
line,
yeah.
The expectation is over y given x and expectation of d. So if you look at that top left corner there, there's 2 expectations there. And so nothing, we didn't change expectation y given x to the expectation with respect to d. It's just one of them doesn't matter anymore. One of them dropped out.
Yeah, because we don't have a, yeah.
Thanks.
Great. Thanks, Kevin. Okay. So, right, if we want to think about this second term, right, this learning error, right, the learning error actually has a couple different parts too, right? We were sort of saying the error that our estimations, the squared error our estimations have, sort of has irreducible error, which comes from the fact that, for a particular x, there's still stochasticity in terms of what the sales price is, right? It's not a single value, like that every household on November 3rd sells for exactly $726,864. Instead, there's some distribution. And then there's learning error, right? There's error that is caused by using too simple of a model, right? Maybe you were using a linear function when the relationship is much more like a quadratic, or maybe we don't have enough data to pick a good quadratic model, even if the representation is quadratic, because maybe we have many fewer points than the dimensionality of the model we're choosing amongst. Okay, so this is just the same term, right? This is the learning error. And again, we can complete the square by just adding and subtracting the same term. Okay. And then we can do exactly what we did before. We have this same eta x minus eta d f hat of d x squared, right? Plus 2 twice the 2 middle terms, right? So if we call this a and this b, right? Then we get a squared plus 2ab plus b squared again, right? So completing the square is a pretty standard technique for moving from one expression in terms of expectation of squared error to another. And it's often very helpful in looking at sort of different interpretations, right? We're not doing anything particularly fancy here. We're just manipulating this learning error into a format that gives us more intuition as to the components of it.
Jamie, Yao Yan has a question.
Yeah, absolutely.
I have a question about the eta. So I wonder the yx here refers to the observation, or is just refers to y and x in general. Like for the house price prediction questions, we only have a list of house prices. It doesn't refer to all the houses. And I was wondering, for the equation for eta, when we're looking at x and y, is that just our observation, or is all the potential, all the x and y, all the house prices and feature sets?
Yeah, so capital X and Y refer to random variables drawn from the set of all hypothetical house sales, right? Little x refers to a particular value of date of sale we could be referring to. And this is something that's a little difficult intuitively, right? Because houses aren't something that there's an infinite distribution over, right? Really what we have is the set of all house sales that happen in a given city, right? That's a set. It's not, in theory, you could have that entire set available to you, right? But yeah, so little x is just a particular value. It could refer to a particular house sale, or you could be hypothesizing one that doesn't actually make sense, right? But yeah, so expectation of y given x is saying we're imagining drawing a new house that sold on November 3rd from the distribution over houses that could or would or have been sold on November 3rd, and looking at the distribution over sales prices we'd see there.
Okay, that makes sense. Thank you.
Okay, great. Okay, so it looks like we're out of time. We have one more minute, but I don't think it's probably fair for me to try to do the rest of this derivation for you. So we're pretty close to describing precisely the bias-variance trade-off we want to talk about, which is basically some way of representing this learning error that we were talking about here as basically two terms. One of which is sort of how different is your prediction from zero training error, right? And for higher p, right, when you pick a really high dimensional prediction relative to the number of samples you have, you can make sure that you don't have any training error. On the other hand, the actual function you'll learn if you imagine redrawing your training data might be quite different if you think about a high p, right? So the variance would be high even if the bias is low, right? So we'll talk more about that at the start of Monday, and then I think we'll move on to ridge regression. So, all right, thank you, everyone. I'll stick around for some questions.
Yeah, I have a question.
Yeah.
So in practice, we don't really have an eta, right? Like we can only estimate that eta given our data, right? Would it be possible?
Yes. Yeah, that's right. Yeah. Right. So we don't have sort of direct access to the distribution in practice, and we therefore don't really have direct access to eta either, right? We could think about sort of trying to learn eta, which, maybe what you would want to do is say, for a new x, if I've seen other x's with the same value, I could just predict the average value that I've seen so far. Now that has a bunch of problems, right? In terms of how accurate it will be. Yeah. And it would require, for one, for you to have at least one sample from every date you might ever see. And furthermore, it's a fairly sensitive estimator, right? Yeah, right. So you don't have direct access to eta x. And that's that's why we're generally learning over this. That's why we generally think about learning over a set of restricted functions, f hat, or sorry, capital F, picking a little f hat from capital F.
Okay. So would it be possible to then compute the expectation of the learning error if we don't, or would we just take the estimate of the eta and then compute the learning error?
Right. So the question is, like, we understand that our training error is not equal to the error we would expect to see in the future. But how do we even say what the error is for some f hat that we've learned, since we don't know eta and we don't know the distribution directly?
Yeah.
And the short answer is that your training error is an overly optimistic estimate, right? Because for a variety of reasons. But there are ways to correct that, basically add terms that penalize more complicated models. And we'll talk more about that throughout the class.
Okay, all right, thank you.
Yeah.
Hi, I'm still kind of confused about the difference between f hat and eta, since they're both supposed to be mappings of x onto y.
Mm-hmm. Yeah. Yeah. So they're both mappings from x onto y, and they're both trying to do the same thing in some sense. But f hat is just a function of our training data, not the entire distribution. And furthermore, it's restricted to belong to some set of functions f that are nice, right? Or that may be nice, right? But like eta can be any function. Eta could be, eta could be like a non-convex function. It could be some like weird sinusoidal thing. There's no reason to expect that eta will be a well-behaved function of x. Whereas f, we generally think about learning f hat from a collection of nice functions, linear functions, polynomial functions, something that we sort of, this isn't always going to be the case, but like in general, something that's not going to be able to have even necessarily zero training error, let alone say, very low error on the underlying distribution.
Okay, thank you.